Hello, I am Maarten Blaauw, and today we're going to discuss age-depth models, where we have some dates of a sedimentary core and then trying to produce curves through those dated depths in order to arrive at chronologies for our sites. We're going to discuss classical age-depth models that were quite popular up to around 10 years ago, and then also the more recent Bayesian age-depth models. I'm going to assume during this talk that we're using radiocarbon dates, but that's not absolutely necessary. Um, these age-depth models were developed for radiocarbon dated cores, and calibration of the radiocarbon dates is done within the software, but we can also handle other types of dates, any absolute dates that come with their uncertainties. Or you can also have let to 10 dates or calendar dates or other types of dates. And it can also be a mix of approaches. I'm going to show several animations, and you're welcome to use them in your own teaching or research. And you can download them from my website or from YouTube or Vimeo. And if you want to go along with the code, if you want to run the R code that is shown during this presentation, you can do so by copying the blue R code onto your own computer in your R session. In order to do so, you would first need to install three packages. That's clam, rbacon, and rplum. Before we start on the A-step model section, we still need to discuss a little bit of how to deal with radiocarbon dates and calibrated dates. On your left here, you can see how a radiocarbon date on a radiocarbon date scale gets pushed through in green the calibration curve in order to arrive at this very weird multimodal calibrated distribution. If we actually calibrate a date in software, for example in R, you can see the code below here. You'll see then the uncalibrated date is really nicely distributed as a normal distribution, we hope. But once it has gone through the calibration curve, it ends up being a multimodal, very asymmetric distribution. And what the software does, it produces an age-depth model, and then for each data depth, it then finds a calendar age and sees how well that calendar age corresponds to your date. So in this case, to illustrate that, I've sampled 100 different ages from this distribution, and the chance of a single calendar year being sampled is proportional to how high his calibrated distribution is at that year. So you'll see that higher probability calendar years will be sampled more frequently than bits where the calendar year is less likely to have happened given this date. Once we've established that, now let's move on to age-step modeling. What do we do when we produce an age-step model? We try to reconstruct what has happened to our site, how it has accumulated in the past. And why we do that is because we have some sort of a climate. It can be, say, temperature, where sometimes it's cold and sometimes it gets warmer. And that would then steer your vegetation, your ice core, your ice sheet. And the vegetation and ice sheet surroundings then cause the mud accumulating in the lake to have distinct values of their proxies. For example, the color, where when there's more vegetation there will be a darker color, more organic material. And then thousands of years later we come to that lake, we drill a core, and then from the colors and other proxies that we see within our lake, we then try to reconstruct what happened with the vegetation, with the ice, and eventually with climate. And for that we need to be sure about when specific things happened. We need to be able to translate our depths to dates, and that's what age-depth models do. So if we think of a core, where here on the vertical scale we've got depth, 800 centimeters depth or so this core has, and it has a handful of, a few handfuls of radiocarbon dates going back to around 16,000 years ago. And the core might be longer than where we have dates, so we might need to do some extrapolation as well. Now, what we can do is we simply can connect the neighboring dated levels, simply by linear lines connecting the dots. That's your very basic classical model, and it used to be the most popular one. Simply linear interpolation between the dated levels. And then you can simply extrapolate back in time by assuming that the thing went straight on further back in time. Okay, that's a model, and it has some issues in that there might be some very abrupt change in accumulation rate happening at some times, and that might be a bit hard to sell. So you might also then start to think about other models. For example, you could kick out one of the dates. Something could have gone wrong with the date, so we kick it out, and then you end up with a model, an age model, which is a bit less varying, is a bit more constant. So that might be a good thing. Or we can assume that there is a hiatus, so our site is accumulated and then something happened, causing a lack of accumulation or removal of sediment for a few thousand years, and then it continues on. If so, then we can also just have these two sections and straight lines through them. Or we can go for a higher order polynomials, why not? Or for example a smooth spline. But in this case, this model causes a reversal to happen, which is very unlikely, we hope. So this is a model we would not want to accept. But classical models don't really have anything prohibiting such events happening. For that we need to go to Bayesian models, which we'll look at later. Okay, so when we have those models, we can what we do is we sample from our dates, as we saw in one of the first slides. We sample from the calibrated dates from each date and then just draw a curve through it. That's one way of doing your age-depth model. And then you simply repeat that process many times. And that is very easy to do in software, where within a few seconds you can get thousands of iterations, thousands of age-depth models. And then for any level, for any depths, be they dated or not, you can then get a thousand age estimates for that depth. Yeah? And from that you can then get a histogram, and from that you can estimate the best age and also a distribution of ages and ranges of ages. Now, this linear interpolation model that has been so popular has some major drawbacks. In that, the further away from a dated level you are, the more precise the model seems to become. So the fewer dates you have, the more precise your model becomes. And that seems very counterintuitive. And that's because a straight line hardly ever happens in for a long time, for over long bits of core in real world cases. So instead you would want to have something that is not straight but that deviates further away, where there's less information. So something that goes its own way if there's no information to constrain it, but then bulges or goes back to more constrained levels where there is information. And that's the type of models that Bayesian models provide. Bayesian models, there's a lot of different types of Bayesian models, and one of the Bayesian models, one of the most commonly used approaches is that of enforcing chronological ordering. We've already discussed that there can be classical age-depth models where there's a reversal, and in the Bayesian model we can quite easily impose that there should always be there can be no reversals at all. And if we take such an assumption, which is very easy to defend, we can then get age models which are more precise sometimes than the underlying individual calibrated ages, and it can also kick out outlying dates. More advanced Bayesian models use that approach, but more than that, they then sample from Oxcal's P sequence, for example. It makes an HF model by accumulating little droplets, virtual droplets of water, and by that it accumulates a core. And you can set the size of those droplets to be of a specific size, so you can get then more smooth or more abrupt age models. P-sequence also has automated outlier detection and removal features, which you can see in this graph here. Another approach is that of B-chron, which is very popular for sea level change studies, and it does a similar thing in it that it accumulates randomly. It takes steps in depth and then steps in time, and does that many times, taking into account that it can never go backwards in time. Yeah. Then we also have Bacon, which I have produced with my colleagues, and this divides a core into many different short sections and models the accumulation rate within each section as a linear accumulation rate. And it has constraints on this accumulation rate. It can't be too fast or too slow, and also it cannot vary too much from one section or one depth to the next, and that those constraints can be set by the user. We also have produced Plum, which is a new approach where you can use LED to 10 data, a sequence of LED to 10 data down core, and using the same approach as Bacon, but then additional to that, it also models the LED to 10 background or supported values and unsupported values. And by taking them all together, it can then produce a Bayesian LED to 10 chronology, and we can easily include other types of dating information such as radiocarbon or cesium or other things. So, to sum up classical versus Bayesian models, we have very little time, but say classical models, they're very fast. You have thousands of iterations within a few seconds, and they also seem to be very precise, especially at low dating densities, so there's no point in getting more dates. Whereas Bayesian models, they take longer to run, minutes to sometimes longer than that, hours sometimes. So they're slower, and they also seem to reconstruct larger uncertainties, especially when you have low dating densities. Well, whereas the classical models have very high precision sometimes, but this precision, even though it gives that precision out, that's what the model does, this precision is often illusionary. And there can be large offsets between the truth and what the model provides. Whereas Bacon models, they show high imprecision levels, but they actually seem to be, if we look at simulations, those Bayesian age models seem to be very accurate. So they have very realistic estimates of their precision. And with classical models, if you add more dates, you don't really learn anything. You don't benefit from more dates, from more information. Whereas with Bayesian models, each additional date will tell you something more. With classical models, if you have outlying dates, if you have scatter, that can be a disaster because you have to take many decisions, many heuristic decisions. Whereas Bayesian models can handle outlying dates very well indeed. Sometimes up to half your dates can be outlying, and the model can still produce a reasonable chronology. So classical models are still popular, but I would say that they don't really well suited to their tasks anymore. There are better approaches there, and that Bayesian age models actually outperform classical models, not only at high data density, but at all data densities, and especially actually at low data densities, which are very common actually. So Bayesian models really seem to outperform classical ones. I want to finish off with a slide where classical and Bayesian approaches are compared in, say, the general dating literature. And to your left, we've got generic radiocarbon calibration software, where in red you have a Calib, which is an online software where you can calibrate individual dates in a classical way. And that came out in 1986 and built up a good um, amount of citations per year to that software. But then it plateaued out around 2010 and has gone down a bit in citations per year to that software since. Since 1994 or so, there has been Oxcal, which has become very popular for calibrating radiocarbonates, especially multiple radiocarbonates in a Bayesian framework. Very popular, especially among archaeologists. And that has really grown into popularity, receiving over 1,000 citations per year. That image is replicated if you look at specifically at age-step models. So CLAM, as the most popular classical age-step model approach software, became, that's here in red, became quite popular until 2015. Since then it has plateaued out. It's not really increasing anymore. The community is still citing it, but not that much anymore. And instead, Bayesian models such as Bacon in dark blue, Bcron in middle blue, and light blue, the P sequence of Oxcal, all of them together show that the Bayesian models are really taken up by the community. Yeah, so something is going on, and I'm happy with that. I think Bayesian models do a better job. So this is me for now, and if there's any questions, we can take them up at the session. Thank you.